This is MEC382, challenge number 2. The original manual process involved an operator taking each shape and counting it by hand. With the job of counting 50 shapes per batch, this can be quite the task for the mind and body, and the goal of this vision system is to reduce this toll while meeting or exceeding the overall time for the operator. As you can see, this is the system that was used for challenge number 2. On the top, you can see that the camera is placed into the light box. The light box allows for reflection of light and also keeps the light from the exterior out. It was crucial to isolate the camera system from the exterior environment due to the flickering lights inside of the building, which can be a common occurrence for some applications. We can see the object is being placed into the white box on the upper right corner on the laptop. This is the region of interest. We also just saw our first part pass inspection as a white triangle, and then this count was then added to the count of large white triangles, giving this system the ability to count by type. The region of interest was chosen due to the finish on the shiny shapes. Being placed in the corner allowed the shiny finish shapes to have a more standardized finish count due to the light reflection being minimized. The overhead diffused lighting was also chosen due to this shiny finish, and the transparency of the shapes did not allow backlight to produce enough contrast. Due to the technique of counting pixels used in this application, and to not reduce orientations available, only one part is able to be processed at a time. However, 90% of shapes, besides those with shiny finish, can be placed in any orientation inside of the region of interest. Here's an image of the fixture that was used to keep the camera stable and also to get a stable image to keep the pixel count consistent. This project was completed on the OpenMV H7 with a QVGA resolution that consists of 320 by 240 pixels. The electrical circuit for this project was very small. It only consisted of a button that initialized the snapshot. This button was signaled from pin 7 on the OpenMV and completed the circuit with a ground. The camera system receives data through USB 2.0 and 28 AWG wire was used for the electrical circuit. The field of view for this project was designated by the size of the shape, which was 1 inch for the small shapes and 2 inches for the larger shapes, but the light box provided an adequate amount of distance from the part for recognition. The backdrop chosen for this project was a brown bag. This brown maximized contrast between the white and black, acting as a neutral color between the two. With the operator still in place interacting with the system, this makes this a human-to-machine interface. The human must initiate the snapshot and allow for the recognition process to occur undisturbed with the door closed. The operator will be able to view the object before and after the snapshot. The operator will be in charge of maintenance of the camera system, which includes replacing lens, cleaning the lens, and removing any dust from the interior of the enclosed environment. The OpenMV H7's camera lens is rated for 3 to 4 years of use along with its sensor, but will require being replaced soon after this duration or if excessive damage or use occurs. As far as mechanical features of the system, besides for the printed camera stabilization fixture is the light box itself, which is a 12 by 12 Decluse light box that has an LED rating of 40,000 hours of use. At this point, we will increase the speed of the video and continue with more part and presentation and speak about the software once we reach an applicable point. Until then, we will continue to process the parts. The original length of this process was 20 minutes to process all of the shapes. Here you can see one of the shapes with the shiny finish that posed an issue with the reflection of the lighting, changing the pixel count. And as you can see, the presentation of this shape is more critical. This part must be pushed as far into the corner as possible to minimize as much light reflection as possible. I'm also replacing the current part with the next one in the exact same position to maintain this position and maintain the pixel count. Though underneath the shape, there has also been a lightly marked dot to provide a standardized placement of the shape to maximize the success of the recognition system. This dot is acting as an unnoticed fixture that does not add more pixels to the image or the region of interest. This light box also has the ability to adjust the lighting to reduce the light reflection, and the system was found to be more successful when reducing the lighting by 2 adjustments on the light controller. As shown, we were able to detect shapes that include this finish and categorize them into their particular shape type and also count them towards their natural shape, color, and size. In this case, the shape was a large black triangle. Though this program was counting and categorizing the shapes, due to that last error, I did lose the total count of the shapes, which was 50 shapes, but this would have been preventable if I added an else statement that printed this as a shape out of range that didn't reset the count by the system. What occurred here was a crash due to the parameters being found were outside the ranges provided. This shows the importance of error-proofing the vision system to allow it to accept error. This completes the acceptance test and ushers us into the code used for this project. This software runs off OpenMV's open source software and uses the Python programming language to complete its computations. Here's the code that was used for this project. We first import the libraries, and then we initialize the camera sensor, but resetting the camera sensor to prepare for the image. We turn on grayscale for maximizing contrast. We set the resolution to QVGA, and we skip 2000 frames for stability. We turn off automatic gain control, and we also turn off automatic white balance because these can both cause issues when trying to count the pixels. We create a dictionary to store the shape, size, and color from the scanned object, and we start the count at 0. We have a dictionary mapping the color codes produced from the blob.code. Black produces a 1, and white produces a 2. The dictionary mapping for the blob.pixel to their shape. 0 is a triangle, 1 is a square, 2 is a circle. And then we also have a dictionary to keep track of the recognized shapes, and we also start the count at 0. We initialize the button on pin 7, and we use a pull-up command to set the floating integer as a 1 or a 0. In this case, it'll become a 1 in its open state. We adjust the delay for the image capture. This just delays how fast the camera takes a picture or snapshot. We create thresholds for the image. These are the color thresholds that determine which color the shape is. So if the blob code is between 0 and 60, it's black. If the blob code is between 200 and 255, it's a white color. So then we use this data in the function to print the color based on a code using the function def colorizer. We add the ease variable in here, and if ease is equals to 1, we print black, and if ease is equal to 2, we print white, and that was mentioned up here with the white and the black. And this is all coming from the blob code that's being fed into the function. We then create another function called Shapify, and this utilizes the blob.pixels command, and this function finds the amount of pixels from the object recognized and sees if these amount of pixels are within the range. And if they are within the ranges, then the shape is determined. So we look here and we decrease the shape by 1 to reset these variables for each loop. So each time the shape goes up and the size goes up, we then reset these values. And then we make a dictionary mapping the shape and size of the colors to the names. So 0, triangle, 1, square, 2, circle, and then small and large. And then as I mentioned, so if it's between 4,000 and 5,500 pixels, it's a large triangle. And if it's above this, it's a large square. And then if it's between 3,400 pixels and 3,700 pixels, we return a large circle. Between 1680 and 1900, we do a small square, and so on. And then, as mentioned in the earlier portion of the video, this was added, no shape detected, and this is just error proofing the system. So we assign the shape to return, and then we return, and then we enter the while true loop. And if the button values equals 0, so in the closed state, and then we take an image and we assign this to image, and then there's a time delay for each image taken. And then we iterate over the detected blobs found in the image, and we feed it the thresholds, the pixel thresholds, and the area thresholds, and we merge the pixels. And then these two were for troubleshooting. These were to print the amount of pixels and the blob code appearing so they could be used in their conditional if statements for the decision. This was mostly just to detect if it was between these ranges and to create the ranges. We then call our colorizer function that's being fed blob code, and then we call our shapeify function that's being fed blob.pixels, and we assign this to return underscore s, and then we add to return underscore s, which is return shapes. We include the color to the shape and the size information, and then we increase the count of return s in the object list, which is here. So this iterates this by 1. So that gives you your count of your shapes. And then we print the shape that has been found and the object list count of how many of these shapes have been found. And that completes the code for this project. The last thing worth mentioning is up here, we had to create additional ranges, and some of them were pretty narrow to fit in the shapes with the finish, with the shiny finish. But to complete this, that's all we had to do was create additional ranges and narrow some of the other ranges. And it was able to see these objects. That in addition with putting the object in the corner, we were able to receive a more standardized and more similar pixel count, allowing for the object to be detected more easily. But that's everything. Thank you for watching.